Well, hello, this is an after Café presentation. We're going to be discussing how to improve device quality. Basically, we're going to be looking at one of the issues that can occur during thin film or device manufacturing related primarily to thin film adhesion failures. So in the creation of devices, whether it's in the research or in the production environment, it's often we're going to find that there's been some form of a failure, and a lot of times these failures are picked up by a number of different means. It could be through an electrical measurement. It could be physically seeing something has failed, as kind of you can see here on the left slide where there's been a wafer that's completely broken on coating, and we'll see an example of that later on in the talk. Or you'll see on the right there where there's been some in an optical image, we can see some ruptured up towards the edges of the wafer. These are very egregious failures. Often the failures we're going to see are much smaller scale, or don't even get picked up by eye or get picked up by any kind of a normal scan until testing occurs, or sometime in use. It could be that the failure occurs from actually a device has been made, has been used, has been cycled anywhere from a few thousand to a few million times, and then we realize there's been an issue, and after in a very careful investigation we realize that there had been a delamination. And it could be that we find that a certain percentage of the production has those delaminations, and we're trying to understand what was the original cause. And so, as you'll see here, I kind of have some bullet points of what some of these causes are. They could be related to mechanical. This could be residual stresses that were built up and eventually caused failure. It could be from thermal cycling. There could have been something chemically going on that either was evolution of the material, so that the material ends up being some form of a heat sensor, and it goes through multiple cycles, and as time goes by, either something has evolved through it, which we'll cover again under environmental, or there could have been something that actually came out of the material changed, and that caused the delamination. Or it could be something, contamination that was on one particular surface of a thin film stack, and we eventually cause an adhesion failure there, and I'll show you an example of that as we go along. So here's at least one example from a paper where during different processes that they had gone through, they started seeing changes in the morphology of the material. So the material went down and everything looks fine, but as they were going through, they basically started picking up some electrical issues, and when they started inspecting on these, they found very physical delaminations were occurring. Another type of a defect, this is something that often is kind of examined, is where someone has made a bond interface, and they're seeing that there's been some form of electrical contact that's not quite making sense, and when they do a cross section, they'll see actually, like you'll see here on the left, that there's delamination across an interface, where normally, or in the case another one here where you're seeing delamination across the top interface. And so understanding what's causing these delaminations, in both of these cases, the delamination, at least from the first appearance, extends quite a ways out. So part of the testing we're going to be trying to do is to try to determine what was the root cause. Where did the delamination start? And in the end, what may have happened, so that we can either redesign the device or look for what occurred during processing that resulted in this device failure. Looking at this other scan down here, someone has put down spin coating, and they're seeing, depending on what the loading of the material is, different levels of delamination as they go through the material. And so you can see it's basically, they're actually seeing this through dark field optical microscopy. And it's important at this point to kind of point out that a lot of times we'll find that there's a delamination, maybe it's by some electrical measurements, and we're trying to determine where the actual delamination is, because a device or a full package can be quite large compared to where the actual defect size is. So often the trick is trying to find where are these at. An example of that is actually in this problem here, where from an electrical measurement we knew that there was a problem with this device. Yet when we went and looked at the device areas by typical SEM, as you'll see here at the 10 kV image, there's nothing apparently wrong with that sample. Yet when we raise the energy up to 30 kV, we're actually punching through to the different layers of the multi-film stack, and all of a sudden we can not only see some delamination, we can see cracking. Another option is a little more difficult because this may require doing multiple steps, but if you have a large thin film, you fully believe there's been some failure, and yet your other methods so far haven't picked them up. And it could be the defect size is so small that something like an XRT does not work, or that the power of the SEM wasn't high enough to go down. And so now we're going to start looking for, can we find this through point-to-point? And a quick way to do this actually can be done through nano or micro indentation. So in this case, these are nano indents where someone is poked through, and we'll actually image the Vickers indent after the fact, and we can actually look at the haze of the defect to see where or not there's been failure. So this is a nice example that was given, and reference is shown here in the slide. So I'm going to go into at least one example of a failure that we are still currently working on, and there will be a subsequent presentation given later where we'll resolve this even further. But we knew that there was a group here that's trying to put down a laser titanate or PZT film, and they have a desired final thickness, and I won't get to that in this slide, but we aren't making that thickness before we're seeing thin film failures. And there's been a suspicion that the failure is being caused by the platinum layer due to looking at cross sections after the fact. And so one of the things we were looking at here, and I'll be fair that in this example we are purposely choosing 3 methods of evaporation or sputtering to put down the platinum layers, and we're letting the platinum layers be a little bit thicker than we would normally put down to try to promote the failure. So we're just trying to see if we can determine what the failures were, can we figure out what surface the failure is occurring at, and finally can we come up with a solution in the long term for putting these films down. So in this method, we're going to take this film of, an SiO2 stacked 4-inch wafer. We're going to clean this material, and then we're going to be putting down our platinum, and after platinum we're going to clean it again before we put down the PZT. So the end goal here is to make sure that if there is a chemical reason for the film failures, we want all the processing to be the same for putting down the PZT layers, as well as many cases we're trying to eliminate impurities. So you'll see here this is an example where after we put down the coatings, and I'll show you some future pictures of, again, with some further failures of this, but the whole point of this failure mechanism was that they put down multiple layers of the PZT until they saw failure. And so in in one case here, it actually enough layers went down to cause the wafer to actually crack. So these are the 3 different layers. One was put down by evaporation. These are all roughly 100 nanometer platinum layers, and then there's been different layers of PZT spun down and then cleaning between each layer. So each layer was about 80 nanometers, and the samples were inspected between them. And so after the first layer, they all looked fine. After the second layer, we started seeing delamination occurring on the evaporated film. Then there had been a low temperature platinum sputter deposits. This is room temperature, 100 nanometers of platinum was put down, and they were able to go 5 layers of PZT before we saw any discolorization, or, and actually you can see here to the upper right of that middle slide here. So in this area here, we can see that there's been some delamination. And then finally, on the high temperature one, everything looked fine until we got to the 7th deposition. So the films looked nice and clean, and then we got to the 7, we saw the thing crack. After cracking, all of this discoloration that you're seeing here occurred. And we'll get to the reasons for that in just a moment. So to start with, before we get to those, let's take a look at what happened when we did these depositions of the film. So we started with an evaporated, and then a low temperature sputter, and then a high temperature sputter. And you'll notice just by looking at top down, these are all images that were taken at the same magnification, and you'll see very large differences in the crystallinity of the material. In addition, what you'll notice is that for both the sputter samples, they're much flatter. That actually been very rough on the evaporated. To some thought, it might be that having a rougher evaporated film may have actually helped with the adhesion, but as you're going to see in a moment, that actually caused the film to be under more stress. Again, we're going to look at the cross-section of this real quick before we get into some of the stress measurements. And you'll see that on the evaporated film, and as it turns out, the low temperature sputter is something similar to this as well, that not only do we see multiple grains, but within the depth, there actually is more than one grain. So it's different grain sizes, but also different grains going through. Whereas with the high temperature, the grains were larger, but they also are singular colorimetric throughout the film, even though, again, this is thicker than we normally would put down. And now we're going to look at just trying to measure the stresses. So before we put the PZT layers down, we actually went ahead and did an optical profilometry, and you could have done the same thing with a stylus profilometer. And we basically looked at the curvature of the wafer after the different films. So the standard wafer before they put down the 500 nanometers of thermal oxide was fairly flat. It wasn't worth showing this image because total amount of deflection was less than a micron. But after putting down to 500 nanometers, we actually left the sample under stress, which gave a minus 12 microns of deflection at the height. But after we put those films, as you can see, the wafer's completely deflected in the opposite direction. And so there's 55 microns on the evaporated, 25 on the, roughly 25 on the low temperature sputtered, and about 15 on the high temperature. And so you can kind of imagine part of what we're seeing is response to temperature, and another part of the response is just how the material is going down. So how we actually can measure this is we can use a fairly well-established equation called the Stoney equation, and we can look at the deflection. We know what the film thicknesses are. We can measure or determine some of the properties in terms of the elastic responses, and from that we can basically measure stresses. So in this image here, the top one here in the measure stress is minus 0.09 gigapascals. That was for the thermal oxide. For the evaporated film, we got 4.2, so we had the highest, and then under low temperature and high temperature, 2.2 and 1.7. At this point, none of those stresses are such that we would expect total film failure, nor would we expect the wafers to break as we saw, but we can definitely see that we found some preloading of the sample. So any additional depositions that occur, if that stress isn't relieved, you can imagine you're going to continually build them up. And that's data we will be presenting in a future talk. But for the further examples of this, and including another way that you can sometimes tell when there's been failure, is imagine you have a very concentric wafer. So if you take a look at the bottom two, you have nice uniform film. You'll see that in both cases, you're roughly getting a uniform stress across there. But if you look at the top two, you'll notice that in this deformation that you're getting changes in the deformation shape. And there are a couple different causes, and so I'm just going to give you off to the right there at least two cases of what those could be. And this actually comes from things that I've seen before where it's not so much the mechanism of the film going down, but the mechanism of how the films are heated. Different heating elements are out there, and so in this case, you actually have the same heater, but one where they put they basically put a silicon carbide material between the sample and the substrate to diffuse the heat so that you had some localized heating in one area, but it was more uniform across. Where without that, they were getting the cycling of heating. It actually looks very much like the element of the heater. And so those are things to keep in mind, because that will change your stress profile for how you put the films down. And that may be something you'll pick up in the stress measurement. And later on, you may actually find out that that has a relation to where on a device formation you have a failure. So the entire wafer that was made up, it was cut up, and then you found that, hey, this one group of devices is failing and the other group is just fine. You may come back to a map like this and say, well, okay, now we can kind of see that as we go through the cycling, there's certain areas where there's failures and other areas where there's not. Once we have those failures, we may want to go back and try to have an idea of what was. So earlier I was showing the nano indentation, and that's one way to kind of look for your failure. A more traditional way of trying to get an idea of how the films may be bonding is just doing a peel test. There's a nice other feature of this peel test is that once we've seen them fail, we can go back and we can actually examine by techniques such as either SAM or XPS, so X-ray photoelectron spectroscopy, sorry, or OJ spectroscopy. We can, or even you can use FTIR, Raman. There's a host of techniques, but we can actually go back and measure what was that composition of the surface where it failed. Let me point two things out here. Once the films fail, please don't put the two layers back together again, because that could potentially change what we're going to look at. Try not to have those faces touch another surface because we want to preserve them. Best if you can do the peel test and do these measurements right after the fact. And you want to measure both surfaces if you're going to be looking at what a surface feature is that may be causing a failure. So here's the case where we've done one of these thin film failures. And so there had been a film that had been on a sapphire substrate. We basically allowed them to fail. And then we went back and we looked at the sapphire portion of the substrate. So had this been pure sapphire, all we would have seen would have been oxygen and aluminum. And you can see in this XPS survey spectra, there's an oxygen 1s peak, there's a little bit of nitrogen that was seen, and a little bit of calcium that was seen, but also there was some carbon and silicon. And reality is, once we did a calculation of the carbon, oxygen to silicon ratio, what we basically determined was there had been PDMS on this surface. And so something that had been done in the process had allowed for a silicone to get onto the surface. It may not have something you were expecting. It could have been something that was in a holder, or it could have been someone was using some kind of like carbon tape. It's not well understood, it's not well recognized, but for a lot of tapes, if you decide to use them as a kind of adherent, they have to have a release agent, and a lot of times silicone is used as that release agent. So it's not, at least in the surface side of things, it's not rare for us when we're going to look for a delamination that we end up seeing a silicone. In my experience, it's more than half the time. So here we have another example of a thin film failure, and this is actually going to be different from what we were just talking about with the PZT film. And in fact, we're going to be looking at a failure that's actually occurred due to a chemical change in the material. And so here we end up having essentially an electrocell that was created, and after multiple cycling of the material, they started picking up that there's been some delamination. So here's a good example of that delamination occurring here, and you can actually see it occur in the electrical measurements where in the one set of measurements is quite fine, and all of a sudden there's getting a dramatic change. And so they wanted to have a better understanding of what was going on in that failure. So they ended up working with a group here, Tim Tai being the principal scientist. And on further examination of the materials, where they actually would go through and look at them at different sets of cycling, they would eventually see that they got to a certain point that you would see morphology change. But if we then wanted to go ahead and examine this further, they actually came in and tried to look at the different grains at different areas, and they did this by Raman, and what they found was a change in the sulfur chemistry. So again, something has happened chemically to this material that during cycling that all of a sudden changed the form of the material, and once that happened, you'll see it's recrystallized, and now all of a sudden you have the formation of a delamination. So our final example is going to be related again to that environmental as causes of failure. So here we're going to be looking at a solar cell that after multiple uses has showed delamination. And since this was a concern, since they wanted multiple years of being able to make these cells work and wanted to find a way to try to improve upon them, they sent them into a group to be examined. This is what they had found was that they had escape gas evolution. So as they examine into the actual layers where there had been failure, they can actually see evolution. This is done through an SEM photo, but they can see evolution of sodium and silver in these delamination zones. And this is something I've actually seen before on a different type of material, but on a low E coating, where you end up getting evolution of silver that then comes being exposed to an area where sodium is found, and you get a rapid reaction between the sodium and silicon, and that actually resolves off as gas, and then you can actually, in this case, it's a beautiful picture where they'd actually see the isolated bubbles being formed during this reaction. And so this is a very nice example of like an environmental cause. In this case, it's the changing over of light and then heating, cooling, causing some local cracking, and then the local cracking exposing sodium to silver. Then you end up getting this nice reaction. So that basically concludes all of the this presentation. I will point out that there will be subsequent slides given on further information related to the platinum example. But I'd like to encourage you that if you have failures that are caused by delamination from thin films, keep in mind that there's multiple different causes of those failures, and often it's a little bit of investigative work. And you can look, not only in the literature, but often the biggest problem is going to be in finding where that failure occurred, and then working backwards to what the cause was. And so, I invite you to contact us here at the MCL, or contact my group from Nanofab if you're working on devices, and we are more than happy to help you with this. Thank you very much.